Hello friends, today we are going to start with the next module, that is the ferromagnetism and the antiferromagnetism. We have seen the Curie law in the previous module, that is susceptibility is proportional to the 1 over temperature, right. Now, in case of the and that susceptibility for the Curie law, that is applicable for the paramagnetic material, right. So, here we can try to understand the temperature at which the temperature here we can find out the order and the disorder states transitions. Okay. So, that we call it as the Curie temperature or the transition temperature as well. Okay. So, or the critical temperature it is also called. So, now in case of the ferromagnetism, what happens that it has a spontaneous magnetic moment, means their magnetic momentas are actually they are in the ordered states, means they are aligned in the same directions, and almost they will be having their magnitude is almost same in absence of the magnetic field which is applied externally one. Okay. Means that the resultant magnetic moment is always non-zero in this case, is always greater than the 0 one. Okay. In absence of the externally applied magnetic field, this is a simple ferromagnetic case where the magnetic momentas are order one. Now, this spontaneous magnetic moment suggests that the electron spins and the magnetic momentas are arranged in a regular manner. Okay. So, they are arranged in a regular manner. So, the here order need not be the simple, all of the spins arranged are here in the same cases, except maybe we can have the some other cases such as the antiferromagnetic case, here we can have the we do not have the spontaneous magnetic momenta, or else the that order or the resultant magnetic momenta is spontaneous magnetic momenta is also called as the saturation moment. Okay. Now, let us try to consider the Curie point and the Curie point first, and then we will be maybe next lecture we will see about the exchange integral here. So, here let us consider a paramagnet with the concentration of the n ions of the spin s. So, the n ions having the spin s, and the integral or the internal interactions tending to line up the magnetic momentas parallel to each other. Okay. Here what happens are we are going to postulate the things that the internal interactions tending to line up the magnetic momentas parallel to each other and call such any interactions as a exchange field. So, this internal interactions mostly we will consider the nearest neighbor interactions. So, this pin will try to interact with the other neighbor one, and the its next one and its preceding one above and the below as well. Okay. So, they will just try to interact in this case. Such a field we consider as a exchange field. So, the ordering effect of the exchange field is opposed by the obviously this ordering effect will be opposed, and obviously the magnetic effect will be cancelled or the opposed by the thermal effects or the thermal agitation. And at a particular temperature, if you just try to keep increasing the temperature at the elevated temperature, the spin order gets destroyed. Okay. Okay. So, now, when we treat such a exchange field as equivalent to the magnetic field B, okay, so the exchange field is equivalent to the magnetic field BE. The magnitude of the exchange field, maybe this exchange field is of the order of the 10 raised to 7 Gauss. Okay, this magnetic field intensity or the magnetic field unit is the Gauss. It will be measured in the CGS, or else it will be having the another unit as a Tesla. 1 Tesla is equal to 10 raised to 4 Gauss. Okay. Here we assume that the B is proportional. Here we assume that the B is proportional to the magnetization. We know that the magnetization is nothing but the magnetic moment per unit volume, unless otherwise specified at it is understood to be the value of the thermal equilibrium at temperature T. So, that is another point to consider. If the suppose the domains are present in case of the material, domains in the sense this is suppose the material, then the certain regions within the material have their orientation of the magnetic moment as in the one particular direction, so or in the same direction, but the next region will be having the different direction of the magnetic moment as are aligned. So, these are the domains, and this the magnetization refers to the value of the domain if you just consider the particular material one. Okay. Uh, in case of the mean field approximation, here we assume that each magnetic atom experiences the field proportional to the magnetization. So, the field the exchange field here is proportional to the magnetization. So, B e is equal to lambda times m, where the lambda is a constant and which is independent of the temperature. Okay, it is independent of the temperature. So, now, here the each spin here the sees each pin actually sees the average magnetization of all other spins. So, in truth it may only see the near neighbors, but our simplification is good for look first at the problem. So, let us try to consider the Curie temperature. So, let us see the Curie temperature. It is the temperature above which the spontaneous magnetization vanishes. Spontaneous magnetization means the ordering of the magnetic momentas in a certain direction gets vanishes, or in the parallel direction vanishes, and it separates the disordered paramagnetic phase at the temperature which is greater than the Curie temperature from the ordered ferromagnetic state or ferromagnetic phase at temperature which is less than the Curie temperature. Curie temperature is the Tc temperature, above which the we can have the disordered state, and below which it will be having the ordered state. So, we can find this Tc in terms of the lambda. So, let us try to find out the Tc in terms of the lambda. So, what is the motivation to find out the Tc? Now, consider the paramagnetic phase here. Okay. So, let us consider here the paramagnetic phase, and applied field B A, okay, B A is the applied field, will cause a finite magnetization, and in turn it will cause a finite exchange field. So, what is happening here? B A is applied, okay, finite, and this will give this will cause us the finite magnetization, and in turn it will cause a finite exchange field. So, due to the interactions happening within the neighboring spins, so there will be a exchange field will be produced. And suppose if chi p is the paramagnetic susceptibility, P stands for the paramagnetic one, then we can write down the magnetization mu 0 m is equal to or the B sorry mu 0 m is equal to chi p times B A plus B A. B A is applied field and this is the exchange field here. So, the magnetization is equal to the constant times constant susceptibility times the field, only if the fractional alignment is a small one. Okay. If and this is where the assumption enters that the specimen is in the paramagnetic phase. So, the condition it is imposed over it that the magnetization is equal to the constant susceptibility times the field only if the fractional element is a small. So, this is where the assumption enters the that the specimen is in the paramagnetic phase. So, that parametric susceptibility is given by the Curie law, and that we have seen, that is chi p is equal to C by T. Here the C is the Curie constant. Now, let us try to substitute the value of the exchange field into this equation and try to rearrange the terms. So, mu 0 m is equal to chi, we know that chi p we know that C by T. So, C by T into B A plus lambda into m. Just try to rearrange the terms, and we just try to rewrite the susceptibility in the CGS unit as chi is equal to magnetization upon the applied field, or the field total field or the field applied. So, this will give us the condition. So, m value of the m we can substitute over here, and or else on the other hand we can write down the value of the B A in terms of the m, and m will get cancelled out, and what is the remaining thing is nothing but the C by T minus C lambda. Okay. So, here at t is equal to c lambda, or else we can see its calculation over here, that is nothing but the b is equal to lambda m mu 0 m c by t b a plus lambda m, and thus try to substitute the values, then we can get it the value as such that the chi is equal to c upon mu 0 t minus c lambda, mu 0 will be there. So, just try to think of its units in the CG, whether it is CGS or the SI unit is used here. You can refer the book as well. So, at t is equal to c lambda, there exists the spontaneous magnetization, because if chi is a infinite one, we can have the finite. Okay. So, in that if, because so t is equal to t c, there exists the actually the singular point. Okay. And at this temperature, there exists the spontaneous magnetization, because we can have the chi is infinite, we can have a finite m for the zero applied field, zero applied field. So, B A is 0 in that case. So, we can have the Curie-Weiss law, that is chi is equal to c upon t minus t c, that is provided that T c is equal to c into lambda. This describes fairly well the observed susceptibility variation in the paramagnetic region above the Curie point. Okay. So, this is also called as the Curie point, that T c is equal to c lambda. Thank you.